Hello and welcome to my first video on interpreting graphs. Now that we've made graphs, we need to be able to interpret, analyze, and make use of them. And to do that, we're going to start with this term we haven't talked much about, or probably most of you don't know, this R squared value. The R squared value is a measure of closeness of fit from the data points to the line or trend line you've drawn through them. In other words, it measures how good of a fit the line is for the data. It has values between 0 and 1, and based on what that value is, it tells you the quality. So let's take a look at this example. Here, we have the population of a country versus the area of a country. And as we see, the points here aren't particularly close to the line. In fact, this one is very far away. As such, we have a very low relation. There's a very poor relation between and our line, which means that we have a very low R squared. If you want to, you can think of an R squared like a grade percentage. Lower is bad, higher is good. The closer you are to one, the better the fit. The farther you are away from one, the worse the fit. This has a relation of 0.152. That is abysmal. You come back with a 15% on a test, your parents aren't going to be happy. Heck, you're not going to be happy. I'm not going to be happy. But in graphing and graphical analysis terms, this means that there is no relation. So let's take a moment here and put that on the board. When the R squared value is less than 0.3, it's so small, like this one here is at 0.152, we say that there's no relation between the data. It's not just that this is a bad fit. It is such a bad fit that we think that one doesn't affect the other. In this case, the area of a country doesn't have a particular effect on the population of the country. And this might seem counterintuitive, but it makes a certain amount of sense. Russia, in this particular case, has a very high amount of space where no one wants to live, or no one really can live, called Siberia. Whereas somewhere like London, almost the entire country is inhabitable. Therefore, the area you have. If we wanted to look at data like habitable land or available territory, might be a better fit, but we didn't do that here. So, again, to summarize, R squared less than 0.3, no correlation, no relation. These variables aren't related at all. On the other end of the spectrum, we have the diameter of a circle versus its circumference. And the R squared value here is 1. This means it's a perfect fit. And we can see this right here. All the points are directly on the line of best fit. There's a direct relation. There is a relation between the diameter of a circle and its circumference. You've all seen this in geometry, or even earlier, the circumference of a circle is pi, which is about 3.13, 3.141, I can't remember the rest, times the diameter. In this case, x is the diameter. This tells us there is a trend we can start predicting. Now, you and I know, based on math, that this isn't a perfect relation, but it's a good enough estimate. We can guesstimate, or not even guesstimate, estimate the future with fairly high accuracy. Okay, that's what that R tells us. To be more specific, whenever our R is over 0.7, as it is here, we can say there's a strong relation between these variables. For instance, this is the highest grossing movie of a year if it was a superhero movie based on the year. So as the time goes on, starting from Superman in 78, the amount of money a superhero movie will make if it is the highest grossing movie of the year steadily increases. Now there are some dips, some exceptions. Spider-Man 3 notably falls short of the line, and Avengers Endgame earned way more money than expected. But on average, in general, we can expect that if a movie is the top earning movie for that year, it will follow this trend. It'll continue on. If we were to predict where 2025 might be, it would probably be, follow the line, somewhere around here. That's what the ultimate goal here is. So, to summarize that, let's put that on the board. When the r squared is greater than 0.7, we say that there is a relation between the variables. The first variable affects the other. So, low r squared, less than 0.3, no relation. R squared greater than 0.7, high r squared, there is a relation. What about in between? What about the rest of the potential numbers? Well, let's take a look at an example. Here, I went to various different baseball stadiums with my family, and I looked at the cost of hot dogs and I looked at the cost of ice cream. Both are measured in dollars. And I graphed them. And I looked and determined if the cost of ice cream in a field is determined based on the cost of hot dogs. And if we look at this data, sure, this data point's fairly close. This data point's fairly close. But this one's kind of far, and this one is definitely far, and this one's far. None of them are as far as Russia was off the line in the country's map, but they're not as close to the line as they were with the superhero movies or the diameter and circumference. In this case, when the r squared is between those two extremes, we don't know. We can't say for sure. We either need more data, more experiments, but it's uncertain. So, to recap, first, on the low end of the spectrum, r squared less than 0.3, all we can say is that their variables aren't related. You can't use trends in one to predict the other. There is no relation. And r squared greater than 0.7 means that if you know one set of data, you can predict the other. For instance, with the superhero movies, we can start predicting what a movie in 2025 will earn if it's a superhero movie in the top box office earner. We can predict in 2030, provided the trend continues. But we're fairly confident it will because the r squared value is so high. Likewise with the circumference and diameter, if we know the diameter, we can always find the circumference. It's so consistent, we make a mathematical formula out of it and taught it to you in grade school, middle school maybe. Everything else, all the other numbers in between 0.3 and 0.7, we can't say for sure. We don't know. It's uncertain. We draw no conclusions. We don't want to use it. We don't think we can. We need more data. That's the general summary. That's the main ideas. But we're going to take a look at three kind of oddball cases just to talk about all the fringes. Case one, when your r squared is 0. The problem with r squared equals 0 is that computers don't calculate it well, so you need to be able to visually identify it. Here, it just says number, number, number. But r squared of 0 means you have a perfectly flat horizontal line. In this case, every year I go to the doctor for a physical. Every year since I was 24, I had the same height. 6'4", which is 76 inches. It gives me a perfectly flat line. As I get older, I'm not getting any taller. Sure, back during puberty, absolutely true, but during my 20s, my height is a fixed value. It doesn't change. It doesn't fluctuate with respect to my age. When I get older, that might change. When I get young, if I was looking when I was younger, that would be very different. But during my 20s, it has no relation. The r squared here we'd report as 0, no matter what the computer tells us, because the computer can't do that math. It ends in a divide by 0 error, which is how we get here. The exact opposite scenario is if your r squared is infinite, which is a perfectly vertical line, like we have here. Again, the computer can't calculate that. It doesn't do infinity well. But you can look at it and go, oh, okay, this is weird. For this, I measured the amount of time I spent at work on a given day and how much rain fell that day in inches. And you'll notice I spent the same amount of time at work every day. I get here at 7:30, I leave at 3. But the amount of rain varies drastically. What this tells you, and this does tell you something, not that there's a relation between the amount of time spent at work and the amount of rainfall, is that some other variable is changing. Typically, you will only see this if you don't change one variable, but another variable changes as a result. But again, keep this in mind. This does not mean that there's a relation. It just means that there's something else changing that you're not accounting for. The last scenario is if you have a negative slope. Halo 3 came out and I was very, very happy. I played it excessively. I had the $60 to buy it on release day. However, my friends didn't. And so they waited a few months and they bought it when it started getting cheaper. As time went on, Halo's cost didn't increase, it decreased. And this is a certain trend. There is a strong relation here. It has an R squared of 0.7, but the correlation is negative. As one variable goes up, the other goes down. You can think of this in terms of cost of a product, or the far more common thing I hear students talk about is how enjoyable or engaged in a lesson they are. At the start of the lesson, you're generally fairly there, fairly cognizant, or maybe even at the start of the school day, you're there and fairly cognizant. By the time it reaches the end of the period, or God forbid, eighth hour, you're barely paying attention. Because you've been in school for so long, your attention span is stressed and strained. As one variable increases, time, your attention decreases. This is still a strong relation, but we call it a negative correlation. Not because it's bad or anything, but because the slope is negative. As one goes up, one goes down. These are your three kind of oddball scenarios. But let's go ahead and kind of summarize them again on the board, and then we're done. R squared values range from 0 to 0.1. A low R squared of R squared less than 0.3 means that there's no relation between your variables. A high R squared greater than 0.7, means there is a relation. The middle R squared, between 0.3 and 0.7, you draw no conclusions. Secondly, if you have a horizontal line, no matter what your graph says, your R squared is 0. There's no relation between those. You have a vertical line that's an R squared of infinity. Some other textbooks will say R squared 0, but I typically use the infinity terminology. It means that there's something else changing that you don't have control over. Finally, we talk about negative relations when the line slopes downward and R squared is greater than 0.7. That means that there is a relationship and it is as one variable increases, the other decreases. The example I gave or used was talking about your energy or engagement in a class as time went on. I'm sure you can come up with your own examples.